Okie dokie. Let's today look at another particle physics reaction. We're going to be studying something called a center of mass. We'll have one particle. This doesn't stand for proton. It just can stand for any particle. So one particle plus another particle will form an H particle right here. Okie dokie. So let's get started with that. What we're going to do initially is have the one particle go at a velocity v, and the other particle is the same mass. We'll have them have the same mass and the same velocity. So this will go with a velocity v to the right, and this one will go to a velocity v to the left. Let's go ahead and figure out the, this is the initial picture here. And let's check out the initial momentum, total momentum. Of course, you have the mass, the relativistic mass of this object times its velocity plus the relativistic mass of this object times its velocity. But of course, both the masses are equal and the velocities are equal, so the initial momentum will equal 0. Here's the final picture. These two things will fuse together and create this H particle. It doesn't stand for hydrogen, it just stands for any particle named H. Just use that letter for the hell of it. And of course, if the momentum is equal to 0, this particle will have a velocity of equal to 0 in the final, because if the initial momentum is 0, then the final momentum will be 0. And if the final momentum is 0, the final velocity will have to be 0 of this particle. So that's what we have here. The final momentum is 0. So we're going to look at actually as the energy in the initial, total energy in the initial situation, and the total energy in the final situation. Initially, we have two masses moving relativistically. So there's my 2 for two masses. And here's the rest masses times c squared over the square root of 1 minus v, the velocity squared initially, divided by c squared right there. And so this will be the total energy of these two particles right here, according to relativity, special relativity. The final energy, of course, the object is not moving, so it'll just be the rest mass of Mr. H here, Mr. H particle. And that'll be the rest mass of H times c squared will be the final energy. Okay. Well, of course, the initial energy has to equal the final energy. And if you solve for m0h by setting this equal to this, you will get this algebraically. All right. So that's what we were after, is what the mass total rest mass of the object at the end was going to be, and we discovered that this way. Okay, now we're going to figure it out in a different manner. This was the center of mass matter. We want to confirm that this is the correct answer. So we'll actually do the problem again, but in a different way. What we'll do this time is we'll let the even though we have the same situation, this time we're going to travel on the particle A. And if we travel on the particle A, of course, A will say its velocity is equal to 0. When you're driving in a car, in space where there's no stars, you'd say that even though you might be moving, you wouldn't know you were moving, especially if the windows were covered or whatever, unless you accelerate. But we're assuming constant speed. So we'll travel on A, so its velocity will be 0 according to A. B, of course, will be coming at us at a certain velocity. Because of special relativity, these things are moving near the speed of light. You can't just add these two velocities. For instance, if this was 100 miles an hour and this was 100 miles an hour, A would say, hey, I'm going at 0 miles an hour, and B is coming at me at 200 miles an hour. That only works when the velocities are very small compared to the speed of light. But when we get near the speed of light, the formula is a little bit more complex. And so we'll look at what's called the velocity addition formula for special relativity. So what velocity is A going to say B is coming at him at? Well, it's not just simply v minus negative v, or twice as fast as this. It's a little bit more complicated. Let's write this out. We write v the velocity of B according to A. So that's what these subscripts mean. And the formula, the relativistic formula, is the velocity of B with respect to the ground, somebody who's on the ground, minus the velocity of A with respect to the ground, over 1 minus the velocity of A with respect to the ground, the velocity of B with respect to ground, divided by the speed of light squared. So if we let's jump down here and discuss this velocity of B with respect to A. What's the velocity of B with respect to the ground? That's not with respect to A. Well, with respect to the ground, V is going at a negative V. So the velocity of B with respect to the ground is negative V, according to this picture. How about the velocity of A with respect to the ground? Well, with respect to a person on the ground, the velocity of A is V. So for the velocity of A with respect to the ground, we put V. We're not talking about the velocity of A with respect to A. That's 0. Okie dokie. And then, of course, these two velocities go on the bottom right down here. And if you do a little bit of algebra here, you'll end up with negative 2v over 1 plus v squared over c squared. So we now have the velocity of B with respect to A, and notice it's not simply negative 2v, it's got a factor down here which changes the velocity a little bit, or a lot sometimes, depending on how fast you're going near the speed of light. Okay, let's take a look at our final picture, because we'll need the velocity of Mr. H according to Mr. A. So again, we'll do the same formula. The velocity of H according to Mr. A, in A's reference system, is the velocity of H with respect to the ground, the velocity of A with respect to the ground over 1 minus velocity of H with respect to the ground, a velocity of A with respect to the ground over c squared. These formulas are the same, except that here we were talking about how A sees Mr. B moving, and now we're talking about how A sees Mr. H moving in the final picture. All right. So let's discuss the velocity of H with respect to A. What's the velocity of H with respect to the ground? Well, remember that the ground said the velocity of H was going at 0, so we'll put a 0 for that. So for this, we'll put a 0. Minus, and then what's the velocity of A with respect to the ground? We already talked about that. It's, of course, a V right here. So we'll put a V for this guy. And then, of course, these two velocities go in here at the bottom. And this is our relativistic formula. This is now going to be the velocity that Mr. H is moving according to Mr. if you were sitting on particle A there. And that turns out to be negative V. Alrighty. Finally, we'll look at the momentum initial, and it has to equal the momentum final. Initially, of course, we have particles A momentum plus particles B's momentum, and that has to equal particles H momentum at the end of the experiment. So this is the beginning of the experiment. This is the end of the experiment. These are all relativistic masses, and these are all, of course, the velocity of A according to A. This all is going to be done in A's reference system. So this is the velocity of A with respect to A, the velocity of B with respect to A, the velocity of H with respect to A. Well, the velocity of A with respect to A, I already told you, was 0. If you're sitting on A and all the windows are shut and you're going at a constant velocity, you will assume you have a 0 velocity. So that term goes away. The relativistic mass of B, of course, is m0 divided by the square root of 1 minus the velocity of B with respect to A. And the velocity of B with respect to A was this term right here. So we're going to take, was this right here. It was this, and then this became this, which became this. So we're going to take, this is the velocity of B with respect to A. This is going to be typed in right there, which is right here. And it's also going to have to be typed in for the relativistic mass, so this will have to be typed in down here also. So we're going to take this and put it into the relativistic mass equation. So this will be the momentum of Mr. B. The momentum of Mr. A is 0 according to Mr. A. And the momentum of Mr. H, finally, will be the relativistic mass of Mr. H. We don't know his velocity that he's flying at with respect to A. And the velocity of H with respect to A is this negative V. So we'll put a negative V there. We put a negative V here, but of course it's V squared, and V squared is just positive V squared, so I don't have to put a negative in there. And divided by C squared as usual. Well, if you do a little bit of algebra, I'll let you do a little bit of algebra and solve for this MH0. You will get this same answer that you have here. Okay? So we proved two different ways that we get the same mass. Of course, the center of mass was a lot easier to do than this was, which is why a lot of particle physicists will do calculations in the center of mass system when they're working on a collider, rather than do all this work right here. Okay, I hope you enjoyed this lecture, and I look forward to any comments at the bottom. Thank you very much.